Well, our next subject is to learn how to treat non-ideal reactors with the tools that are available to us. The tools that are available to us are the treatments that we can perform with the ideal reactors. And also, we have learned a tool that will give us the behavior of the black box reactor in terms of the residence time distribution of an inert tracer. So using the residence time distribution of the inert tracer, we can at least guess what type of behavior we might have in a non-ideal reactor. So let us have a dotted frame around a non-ideal CSTR, right? That will represent the black box behavior. Let us have our inert tracer experiment, injecting the inert tracer, and let us monitor the product. But this time, we will know what we are getting and why we are getting that. Now, in this non-ideal CSTR, which is relatively large in comparison to the typical CSTRs that I was drawing, that we might have the dead zones, that the impeller is not sufficiently large to mix the contents at the corners of the reactor, and instead of a flat boundary, our impeller also exhibits a vortex, and this vortex results in the bypassing of some of the fluid without even mixing with the rest of the contents. As a result, we have in part of the reactor a perfect CSTR behavior that our inert tracer will go through an exponential decay. In part of the reactor, we are going to have domains that interact with the rest of the reactor only through molecular motions. By the molecules diffusing in and out of this domain, they are the dead zones. We are going to have bypass domains which will behave like a plug flow reactor. And the probability, the density function, and the washout curve will look like this. So we're going to have a relatively small fraction of this as a CSTR performance. We're going to have a very, very long tail for a dead zone. And then we are going to have a bypass, a sharp bypass which behaves like a plug flow reactor. So add them up, this plus this plus this, our function should look like this. So it is the experience of the engineer that is going to dissect the components into a CSTR, a dead zone, and a bypass zone. But one good aspect of the tracer analysis is the area under these curves are going to be proportional to the volumes. Let me call this A1. Let me call this A2. And let me call this A3. A1 plus A2 plus A3 is going to be proportional to the volume of this reactor, the volume of the contents, and the relative proportions are going to be representative of the fraction of the fluid that is undergoing the changes as dictated by the residence time distributions. The problem with the residence time distribution analysis is that it is not going to allow us to determine which is happening first, which is happening after. Now, imagine that you have a plug flow reactor and a CSTR. In series. In the first situation where we have the plug flow reactor as the first unit, in the second situation, we have the CSTR as the first process unit. When we introduce the inert tracer, here or here, both of these situations will give rise to the same residence time distribution curve. That we are going to have a delay that is going to correspond to the plug flow reactor. It doesn't matter whether the plug flow reactor is before or after the CSTR. Then immediately after, we have the CSTR behavior. We know that we have one plug flow reactor with a space-time of tau1 and the CSTR with a space-time of tau2 dictated by the decay exponential decay. We can identify tau1 and tau2, but we cannot tell whether the plug flow reactor is in front of or before or after the CSTR. This is the problem with the residence time distribution analysis, but once we have the residence time distribution analysis, we can estimate the performance of the reactor, whether we have a plug flow reactor, a CSTR. By making tests and trials, we can identify whether our non-ideal reactor, how is it best represented? What type of reactor configuration represents our reactor best? So this is the simplest approach that we analyze a typical real non-ideal reactor. So far we were talking about perfectly mixed reactors. However, we have to also deduce the mixing quality, and we are going to identify two different mixing forms. One is micromixing, one is macromixing. Micromixing is the mixing that we establish within the fluid element. And here we have ping pong balls representing fluid elements. They are entering with the incoming fluid, leaving the reactor with the outgoing fluid, and these fluid elements, they are perfectly micromixed. Mixing within the fluid element is perfect. But those fluid elements don't mix with one another. In other words, they behave like ping pong balls filled with the reactive fluid. In other words, they are acting like batch reactors, And here in this macroscopic domain, we also have an impeller mixing those small fluid elements, for example, to ensure the thermal uniformity within the reactor. So perfectly micromixed fluid elements behave like small batch reactors. And we have a perfect CSTR here with a washout function of Ci over Ci0 to be equal to e to the minus t over tau, or f of t. F of t was the density function, which is equal to minus dw over dt, and that is equal to 1 over tau e to the minus t over tau. Now I will take this density function. Okay. This is, each of them are acting like a batch reactor. So I will have the batch reactor analysis for the contents. So that I have C of t, let me say Ca of t, concentration of A as a function of time. And this f of t is going to give me the distribution where the average time that each of these fluid elements can spend within the reactor. So if I take this concentration and convolute it with the distribution function of these fluid elements, that is going to give me the average concentration within this reactor, f of t times Ca of t dt for all times. So this is one approach. This is one approach of treating non-idealities. That we have perfectly micromixing and perfect macromixing, but still our fluid elements do not interact with one another. Non-idealities are in terms of the ping pong balls that enter into this reactor. There might be situations where we have imperfections in micromixing, imperfections in macromixing. How else can we treat these problems? Now we have to make sure that we understand our reactor well enough to come up with alternative solutions. For example, let me enlarge a domain of this particular reactor, the inlet domain of this particular reactor. Let's magnify that I have one fluid element coming in. I will call this one 0. Enters into the first domain of my reactor, which is located next to the second domain of my reactor. Then I have nth domain of my reactor. Then I have n plus 1th domain of my reactor. And each of these domains may have exchanges of fluid with one another. And writing a balance for domain 1. I have at steady state F0 coming in. I use smaller f's just to indicate that these are subdomains, plus f from n to 1 coming in, plus f from 2 to 1 coming in, minus f 1 to 2 leaving, minus f 1 to n leaving, to be equal to 0, plus, of course, r times, let me call RA times V1, volume of the first domain. So this is the generalized CSTR equation for domain 1, and I have to write it for all the domains that I have identified within this reactor. And this is called the zone model. And if I have too many zones, of course, analytical treatment becomes impossible, and I have to use tools that are available to me, computational tools that are available to me. Now let us consider a plug flow reactor this time. If we mix our reactants early in the reactor, this is stream A, let us inject stream B at the inlet. This will be an early mixed fluid package which is going to traverse through the reactor without being mixed with the fluid element neither before nor after it. And I will leave the reactor as a perfect plug flow reactor configuration. But what if we introduce B in small segments, little by little? What happens? We have to write our balance equations. We have to know the volumetric flow rate of each of these streams, and we have to write our balance equations segment by segment. All right? So this plug flow reactor operation is very similar, in certain cases, identical to the operation of a semi-batch reactor, where we have one of the fluids in a batch and the other one is added continuously. We have the A fluid package moving along this reactor, and each time it receives a little bit of B. Each time as the conversion, as A, all the reactants are converted, a little bit of B added. As time progresses, a little bit of B added. All right, so those two operations, if this is a perfectly mixed semi-batch reactor, and if it is a perfectly plug flow reactor, they are identical. Okay? So this is one type of operation where we model non-idealities, or we take care of the non-idealities by dividing reactors into compartments that we can tackle mathematically. On the other hand, we have another kind of reactor, a plug flow reactor. Okay, a plug flow reactor where we feed A's and B's, whatever our reactants are, and we gradually remove products. Okay. So here this product was removed after a short period of time. This product was removed after a little bit conversion has taken place, and so on and so forth. All right. This operation is equivalent to a semi-batch operation where we have A's and B's continuously fed, but then we gradually, A's and B's are fed initially and very gradually remove the product. Under the plug flow reactor, perfect ideal plug flow reactor condition, this is equivalent to an ideal, perfectly stirred semi-batch reactor operation. So in summary, we discussed the features of a maximum mixedness reactor, a segregated flow reactor, and two different types of semi-batch reactors. Mathematical analysis is going to be unique for each reaction and for the particulars of the reactor volume versus the flow rates that we arrange. So let us see how we are going to treat some of the non-idealities in a plug flow reactor. PFR. The plug flow reactors, as we have been discussing, were ideal reactors where fluid elements did not mix neither with the fluid element before nor after. So our fluid element remained intact as if it were a ping pong ball, non-interacting ping pong ball, until it left the reactor. However, in real situations, molecules can diffuse forward or backward depending upon the relative molecular motion with respect to the fluid velocity. So we might have gradients in either directions. For example, the reactant A in an A goes to B type of a reactor. The reactant A, as the reaction proceeds, is going to be depleted towards the end of this reactor, and A molecules may rush to fill the chemical potential depleted because of the conversion towards the end of the reactor. On the other hand, there is no B in the initial part of the reactor, and B molecules, depending upon their relative average velocity in the domain with respect to the bulk velocity, they might diffuse back to the inlet of the reactor. So in order to take this into account, we are going to write the reaction diffusion equation. Under steady state conditions, the plug flow reactor design equation was of the following structure. dCA over d tau was equal to R sub A. We have taken care of the volume by bringing it to here and leaving this equation not in terms of a function of volume or a function of position, but as a function of space-time. Now let's take this one and make it a function of position. Let's indicate that this is the z direction. We still have uniform concentrations in our direction, and we are not going to take that dimension into consideration for the first analysis. So we are going to have a linear velocity of u in the z direction. So we are going to rewrite this as u times dCA over dz to be equal to Ra. Let's just have a first order reaction here for the sake of simplicity in the mathematics. But then our fluid, our molecules, are rushing away from our control volume because of the diffusion. dAz times d square Ca times dz square. So this is the reaction diffusion equation. This d is the axial dispersion coefficient. Now let's rearrange this equation. D square Ca over dz square minus u over, I divided the whole equation with the axial dispersion coefficient times dCA over dz plus k times Ca is equal to 0 k over dAz. So in a domain where the reactants disappear through the reaction, the minus sign, the reactants also dissipate through axial dispersion by diffusion. This side of the equation is rearranged by defining tau as z over u, axial position, axial linear velocity. When we rearrange this equation, we have the following differential equation. D square Ca over dz square. I divided both sides of this equation by the axial dispersion coefficient and moved the u term to this side of the equation. Minus u over dAz, dCA over dz minus k Ca over dAz. Now we are going to use a non-dimensional position in order to have a general derivation. I'm going to define a non-dimensional position variable as z over L. So the result of the non-dimensionalization will look like this. D square Ca over the z square minus u L over dAz times dCa over dZ minus k L square over dAz times Ca to be equal to 0. Now there are two important implications in this semi-non-dimensionalized equation. We have two non-dimensionless numbers. One is the Pecla number and the other is the Dam-Köhler number of the second kind. So the Dam-Köhler number of the first kind was tau k, if you remember. Now we have a second kind, k L square over d square. And then we have a new dimensionless number, which is u L over dAz, and this is the Pecla number. So we continue with the relatively cleaned up version of our derivations. Our differential equation is here with a second order term representing the diffusion, the first order term, derivative term representing advection, and the reaction kinetic term under steady state conditions. Now we have to establish two different boundary conditions for the second order differential equation. We need two boundary conditions. We're going to write those boundary conditions, one at z is equal to 0 and the other one at z is equal to L. So further cleaned up version of the species mole balance equation subject to an axial dispersion effect with Dankworth's boundary conditions are presented on the screen. It is going to be your homework to solve this differential equation, apply the boundary conditions, and find the equation that represents concentration of species A relative to the concentration of A at the inlet, or Ca0. Let's write Ca in here. Now I'm going to further discuss a couple of things relative to the Pecla number. All right, so here, this is the Pecla number in non-dimensional form. Now, when Pecla number goes to infinity, means that diffusivity is going to 0, or axial dispersion coefficient is approaching to 0. When the axial dispersion coefficient is approaching to 0, this term drops out from the initial non-dimensional form, you can deduce that the first term, this term, disappears. And as a result, our balance equation takes the following form. U dCA over dZ minus K times Ca to be equal to 0. And notice that this is the design equation of a plug flow reactor. In the other extreme, Pecla number goes to 0. Let's write it here. When Pecla number goes to 0, in other words, our linear velocity in the domain is 0. So this term disappears. That our differential equation takes the form d square Ca dAz dz square minus K times Ca to be equal to 0. And this expression eventually leads to the design equation of a CSTR. All right? Because our dependence on Z disappears, we integrate this twice to arrive at V0 Ca0 minus V0 Ca divided by minus R sub A is equal to V.